Welcome back to everybody. I thought we would spend just a couple of minutes reviewing what we had talked about at the end of last time. Epoxide ring opening, or epoxide opening regioselectivity. Recall that we decided that if the two carbons that are involved in the epoxide, we'll call them 1 and 2, if they're not equal, we have to worry about which one gets the nucleophile. And if we're under strong nucleophile conditions, negative charge, no acid present, and you can use any one of our strong nucleophiles that are on our list. Just for fun today, maybe let's choose some deprotonated alkyne. That could be on our list as a strong nucleophile. We're going to expect that to attack the less substituted carbon because of sterics. The mechanism is, as we said, SN2, and we might talk about the transition state being early, meaning that the nucleophile has to get in there quickly before the leaving group leaves. And so sterics matter a lot here. And that's why you choose selectively the less substituted carbon. I'm showing the final alcohol product that you would get after you protonate the negatively charged oxygen. So this would be our product here, okay? So when you're using a strong nucleophile, it's very SN2-like, and the nucleophile needs to approach closely before the leaving group leaves, and therefore you attack the less substituted carbon. In contrast, if you're under acidic conditions with the same starting material, the regioselectivity switches. I think our example here was using HBr, and so we said that Br will attack selectively the more substituted carbon, and we'll get the O- group, the leaving group leaves and is now attached to carbon number 2, and then it gets protonated and we have the OH group. So differences in regioselectivity. Selectivity for the less substituted carbon, that's where the nucleophile goes, versus the nucleophile coming in on the more substituted carbon. The reason that the regioselectivity switches, recall that the first step under acidic conditions is that lone pairs on the oxygen remove a proton from HBr. That's a typical HOMO attacks LUMO acid-base kind of experience. Then once you have the protonated epoxide, we talked about how as the nucleophile approaches, the leaving group starts to leave from the more substituted carbon because that carbon can better tolerate a buildup of positive charge in the transition state. And this was a point that was maybe difficult to see, so I'm going to try to illustrate it from another direction. Here's that, here's the protonated epoxide. Here's the 6-membered ring and the methyl group. And here is our bromine coming in and approaching from the backside of the epoxide. And what we mean by the oxygen leaves mostly from the more substituted carbon is that our transition state involves a much longer bond between oxygen and the more substituted carbon. So that oxygen's no longer evenly shared between 1 and 2. It's leaning away from 1. As it does that, there would be a buildup of partial positive charge on 1. As that oxygen leaves, carbon 1 should be somewhere in between sp3 and sp2 hybridized. It's going to flatten out a little bit in response to the oxygen leaving, and that will make it easier for bromine to attack. Bromine will prefer to attack at carbon 1 because that's where the positive charge is. So it's this transition state that explains the regioselectivity of this reaction. So that's important to keep in mind for epoxide opening. You can control which of the two carbons gets attacked. Right? Any questions you want to ask about that? Go ahead.
Just to confirm, so the top one is because it's under nucleophilic conditions and the bottom is because it's under acidic conditions?
Yep, you've got strong nucleophile conditions. You're going to open up at the less substituted carbon, and then opening up epoxides under acidic conditions, you can open up at the more substituted carbon. We've said that this reaction is an SN1-like SN2 reaction. And by that we mean, and I can't remember whether I showed you guys this or whether it was in the other class, but if you think back to when we first introduced the idea of SN1 to SN2, we drew sort of this multi-dimensional reaction coordinate energy diagram, and on one axis we had leaving group, let's see, on one axis we had nucleophile attacks, and on the other axis we had leaving group leaves. And remember that the SN2 pathway we sort of drew as a diagonal path where the leaving group leaves at the same time as the nucleophile comes in. And then we had an alternative path in purple where the leaving group left first and then the nucleophile came in, and we had a carbocationic intermediate. The purple pathway was SN1, the blue pathway was SN2. And what we're trying to say for an SN1-like SN2 reaction is a reaction that's still concerted. There's no intermediate. But if you were to put the transition state for the SN2 reaction somewhere here, where the leaving group and the nucleophile are roughly the same amount left, you could explain the regioselectivity for option 2 by just moving that transition state a little bit further down the line in terms of leaving group leavingness. All right, so you just take that transition state and you say, okay, well, what would that transition state look like if the nucleophile stayed where it was, but the leaving group left a little bit more? And so you might adopt a more curved pathway from starting material to product. And so we would say that this transition state is still an SN2 transition state. It's still concerted. There's no intermediate, but the intermediate looks a little bit more like a carbocation, and that explains the regioselectivity. Okay, anything else? So what is the mechanism for option 2? The mechanism is still SN2. Notice that the transition state still involves the epoxide and the nucleophile. So we're still forming a new bond as the leaving group is leaving. We're just saying that the transition state involves a bit more of a broken bond between carbon and the leaving group than our typical SN2 reaction does. All right. So that reasoning is going to come up again in chapter 10 when we talk about another 3-membered ring intermediate called a bromonium ion. And we'll save that for later, but you'll see it again, and we're going to use exactly the same reasoning. So that basically concludes chapter 9. And so we're going to move on to chapter 10 and 11. We actually won't spend a lot of time on 11 because 11 is a rehash of most of the same issues in chapter 10. It's just the nucleophile is only a little bit different. In chapter 10, our nucleophile is going to be a pi bond. Up until now, you'll notice most of the nucleophiles we've dealt with have been lone pair electrons on a heteroatom. And that's why we've done substitution and or elimination reactions. But when we think about the nucleophile is the carbon-carbon pi, well, actually what I mean by this is the nucleophile is going to be an alkene or an olefin. And the highest occupied molecular orbital in the olefin is going to be the carbon-carbon pi bond. So that's going to be where, though the pi electrons are the ones going to be doing the attacking. And there are a few key principles that if you master, all of the details are not actually that difficult. Hopefully you should see the 4 or 5 new reactions we do as variations on the same basic theme. And the first part of that theme is that pi bonds are planar, and they have a top face and a bottom face, and those top and bottom faces are identical, or at least similar if the molecule is chiral. I'm struggling to write while speaking, so let's try that again. Top and bottom faces are identical or at least similar. And so from a stereochemical standpoint, the pi bond can attack an electrophile from its top face or its bottom face. And we'll need to consider the implications of both of those things. It's a simple stereochemical problem, and we'll see examples of that. If you want me to illustrate how the top and the bottom faces are similar for an olefin, we just need to draw a pi orbital again. And aside from wave function sign, which doesn't influence reactivity, you've got the same thing above versus below. So what I mean by that is if there's an electrophile, 2 electrons in the pi bond, if there's an electrophile, the pi bond might attack it from its top face, or alternatively, might attack it from the bottom face. I don't mean to communicate by this that both of those things are happening at the same time. That's why there's this or here. I also don't mean that these electrons in the pi bond are only in the yellow side and not the blue side. No, they are evenly shared between both places at once. This is a standing wave. We're thinking of electrons as waves. Okay. Second, when the pi bond attacks an electrophile, one carbon gets the new sigma bond between carbon and the electrophile, and the other gets a positive charge. So we're going to arrange this. We're going to arrange the connectivity or the regioselectivity of the reaction such that the more substituted carbon gets the positive charge. Okay, so when the pi bond attacks an electrophile, one carbon gets the new sigma bond and the other carbon gets a positive charge in what will have to be a carbocation intermediate. And as we know, carbocations on more substituted carbons are more stable, so we're selectively going to choose to make the new bond between carbon and electrophile such that the more substituted carbon gets the positive charge. And then finally, a stereochemical reminder that carbocations are planar too. And can be attacked from above or below. All right. So what we're proposing here for a reaction in which the nucleophile is an olefin is that the nucleophile attacks an electrophile, we make a new sigma bond, we get a carbocationic intermediate, and then that carbocation gets attacked to give you a product. Let me show you an example, and we'll also talk about energy diagrams and other implications. So here is an alkene. For fun, I'm going to put a deuterium here, just so that we can appreciate some of the stereochemical implications of this reaction. And the electrophile we're going to use is HBr or HCl. And this reaction has a name in your text. It's called hydrohalogenation of alkenes or olefins. And it is the opposite of an elimination reaction. We will call this an addition reaction for reasons that will become clear. So HBr is our electrophile. The relevant orbital in our electrophile is the LUMO, and that would have to be the hydrogen bromine sigma star. The nucleophile is our olefin, and the relevant I said that wrong. Relevant. That's a Horton felt particularly relevant as he sat on the nest. The relevant orbital here is the HOMO, which is the carbon-carbon pi orbital. So we're going to show HOMO attacks LUMO, pi bond electrons attack hydrogen bromine sigma star at hydrogen so that Br minus can be the leaving group. That's step one of the mechanism. Now, a couple of things. We said that you're going to form the bond with the less substituted carbon so that the more substituted carbon can have the positive charge. So that means we ought to put the positive charge on, let's call it carbon 1. Now on carbon 2, we have deuterium and hydrogen, and we're going to need to determine whether we think the hydrogen added from above or below or both. So, what do you think? Above here. What else? And below or just above? Pi bonds are the same on either side, so it's got to be both, right? So we're going to get two different stereoisomer intermediates, one in which hydrogen added from above and one in which hydrogen added from below. Those two intermediates happen to be enantiomers, and they will be equal in energy, right? Have to be. So this is your carbocation intermediate. Then Br minus is hanging around, and it can be our nucleophile. From this point on, it's just SN1 chemistry. The new thing was pi bond acting as a nucleophile, but once you get to the carbocationic intermediate, it's just regular old SN2, regular old SN1-like chemistry. So we're going to have the nucleophile attack the electrophile, and it's going to happen from above or below with equal frequency. So that means that we could get from the enantiomer intermediate A on the left, we could get the following two products. One in which bromine is up and on the same side of the molecule as the hydrogen that we added, and one in which bromine is down and on the opposite side of the molecule as the hydrogen that we added. Okay, and then we could do the same thing from enantiomer B. We could have bromine add from above. Or below. Okay, so stereochemistry time. I've got 4 possible products. Let's explore the relationship between each of these products. And I don't know what to call them, so maybe we'll just give them numbers. 1, 2, 3, and 4. All right, what's the relationship between 1 and 3? Go ahead. Are they enantiomers? Yes, they are. How did you know that was the case? All but one or both? Yeah. So both of these stereocenters are opposite in the product below, and that makes 1 and 3 enantiomers. How about the relationship between product 2, I'm not sure where to put the 2, and product 4? Same, also enantiomers. So the stereochemical configuration switches. I'm using colors here instead of R versus S because I don't want to embarrass myself on the fly by getting R versus S wrong. But now you're going to make me do it, aren't you? No, you don't care. Okay, thank you for not caring. I appreciate that. All right. How about the relationship between 1 and 2? Diastereomers. And same thing about the relationship between 3 and 2 or between 3 and 4. In fact, we can sort of separate these out, and everything here is a diastereomer of everything in here. So yeah, these two are diastereomers. Okay. So we get 4 possible stereoisomer products from this reaction. Because in the first step, attack can occur from above or below, and then that same thing happens to the carbocation. Attack can occur from above or below. 2 options in the first step, 2 options in the second step. 2 times 2 is 4, 4 different possible products. Notice, though, that there aren't 8 possible products. In none of these stereoisomers do we ever have the Br on carbon 2. Similarly, in none of these products do we ever have the proton on carbon 1. So this reaction, we will say, is regioselective for having the Br on the more substituted carbon. And there's a name that your text will use, Markovnikov product or Markovnikov regioselectivity. That's where the Br ends up on the more substituted carbon, and it's because of the carbocation intermediate. You don't have to memorize the name of the dead people who discovered these reactions, but you may want to be aware of that term so you know what your text is referring to. However, the reaction is not stereospecific or even stereoselective. That means there is no favoring of one enantiomer over the other, or one diastereomer, and there's no reason that one diastereomer has to dominate over the other. A couple of terms that we will use for diastereomers that are created upon addition of things to alkenes. If we look at the two things we added across the double bond, one was H, and the other was Br. So you, in the diastereomers on the left, H and Br are on the same side of the molecule, of the same side where relative to what the original alkene was, right? Both of them in enantiomer 1 were added from above. Both of them in enantiomer 3 were added from below. We will call these, this set of diastereomers, we'll call them both syn diastereomers, or syn products, SYN for same. In contrast, over on the right, you can see that the Br and the H end up on opposite sides of the molecule relative to the way it was in the original double bond. And so we will call these anti-products or anti-diastereomers. And for this hydrohalogenation reaction, there is no selectivity for anti versus syn. You get both. Okay, so there's some questions. Go ahead, Hannah.
I hate myself for asking this, but if the two stereocenters were identical in terms of substitution, what would you have?
So if the two, the question here in class is if the two carbons were identical in terms of substitution, then you would have 4 more products where the Br was on the other carbon. One way to show that, to cheat, is just to say, well, what if, let's just have them be the same so it doesn't matter. But I believe you're asking, what if this was an ethyl group? Then yes, there wouldn't be any regioselectivity at all because there's similar substitutions on both sides. So you would have 4 products for where H added to this carbon and Br to this one, and another 4 where Br added to this one and H added to that one. Okay, so some questions from the chat. Isn't D just another hydrogen? Deuterium is an isotope of hydrogen. It's the same size. The nucleus has just got another neutron in it for deuterium. It behaves chemically just like hydrogen, only we can tell the difference. So because we can tell the difference, it becomes a stereocenter. The Markovnikov regioselective explanation is just that the reaction is regioselective for putting Br on the more substituted carbon and H on the less substituted carbon. But the reason for that is easy. It's because you choose the pattern that gives you the more stable carbocation intermediate. All right. Could you make one stereoisomer preferred over another by adjusting the solvent? Well, in terms of enantiomers, no. In terms of diastereomers, that's a great question. It is possible that the syn product could be present in a larger amount than the anti-product or vice versa. Diastereomers, as you recall, can have different stabilities, different physical properties, different rates of formation. So they don't have to form in a 1-to-1 ratio. The two enantiomers do. But the syn and anti-products don't have to be present in a 1-to-1 ratio. What I guess I'm saying here is that the mechanism of the reaction means that you don't have to get one or the other. There's a possibility of getting both, and a complete answer of what the products would be here would include the 4 things that I drew here, even if the syn and anti-products are not present at the same ratio. Other questions? Yeah.
Sorry, can you explain again what those syn and anti?
The syn diastereomers are called syn because the two things that we added, the Br and the H, end up on the same side of the molecule.
Oh, I see, like going forward and back?
Yeah,
Oh, okay.
yeah. So in an enantiomer 1, Br and H are both above the page. They added to the alkene from above. In enantiomer 3, Br and H added from below the page. Yeah.
We previously discussed having a major product
Uh-huh.
and a minor. How do we determine which one's major in this?
Right. The question is, we've discussed for elimination products anyway, identifying major versus minor. Can you do that here? Not that I know of. I think you could probably argue in this case that the more stable product No, I mean, the one place that applies is the identity of this carbocation intermediate. That's why I'm telling you don't get those 4 other products that you could get. But in terms of which of these syn versus anti dominates, it would be difficult to say. Go ahead.
So even by looking at like a chair confirmation of it?
Could you look at a chair conformation and make some predictions? Possibly, but stability of products only really matters if the reaction is reversible and you can go back to an intermediate, and I'm not sure that's the case here. I think once you get the product, I don't think it's easy to get back up the hill to the carbocation. Yeah.
So can we say that the addition reactions that we're talking about right now don't have major or minor products?
Right now, yeah, we can say that the addition reactions that we're thinking about, there's no major or minor product to predict here. Now, there are going to be some examples of reactions where the mechanism is a little bit different, and therefore there is going to be a preference for a syn product versus an anti-product. But because this mechanism involves a carbocation, there can't be. All right, yeah, go ahead.
Would there be anything with the eclipse versus the staggered confirmations for that same thing?
Is there anything, meaning, is there anything about conformations in this product that might say one would be preferred over another? I don't think so. We could draw the chair forms for each of these, and you could probably argue about which of the 2 diastereomers had a more stable chair. Even so, I wouldn't ask you to choose one as a major or minor product. Yeah.
Sorry, this is going to go a little off topic, but with like Hannah's question, if it was non-regioselective and everything, would that affect, and also with like an immune projection with anti and everything, would that affect which products would be more likely to be here, more other minors?
Okay. I'm not sure I understand the question, but I believe there's a bit of a confusion with respect to terms. We are using anti here in a different way than we did with Newman projections.
Yeah.
In Newman projections, anti meant dihedral angle looking down a carbon-carbon bond is 180 degrees.
Yeah, I didn't mean that.
Okay. We're using anti now just to say opposite.
Yeah.
Yeah, we could just as easily use cis versus trans. I don't know why we don't, but now I think you're asking if we tried to do this same reaction. I'm going to do something that grossly simplifies, not grossly, like I meant that in a large sense, not in a disgusting sense. So dramatically simplifies drawing the products of this reaction. I'm not going to use dashes or wedges at all to communicate that all possible stereoisomers are present. I could have done that above, and that would have been a correct answer. I could have easily just done this, but I wanted to show you all of the stereochemical issues. So I think the question that we've gotten is, in the situation shown, is there any regioselectivity? These are 2 regioisomers. And is there any regioselectivity? and I'm not sure, I don't think so. The carbocationic intermediates that you would get are similar in stability, such that it would be difficult to choose whether one happened versus the other. Now, each of these represents 4 stereoisomers, 2 diastereomeric pairs of enantiomers. You could go draw each one and look at all of the chairs. If you want to draw both chairs for each of 8 products, you're talking about 16 different conformations, and then you could argue which chair was more stable. But that's beyond the scope of what we really want to worry about. And in part, that's just because of synthetic utility. You're not going to do a reaction that leads to tons of products if you want it to be useful. But the stereochemical principles here are important and serve as a contrast for the situations where you don't see both syn and anti products. All right, what else? Okay. Yeah, no? Okay, that's fine. Let's see. So, your text presents the next reaction as something unique and sort of on its own. It's just exactly the same thing as we've done here. We're only using a different acid. So as much as you can, it's going to be helpful to sort of group some of these reactions together because that way you won't get lost in all of the details. Look for things that are in common. Your text calls this next reaction hydration of alkenes or olefins. And it's just backwards elimination of alcohols. Or you can think of it as hydrohalogenation, only you're using hydronium instead of HBr. So we can take a similar starting material, and I'm using this starting material not because it's special, but to illustrate all of the regio and stereochemical issues. Using a catalytic amount of sulfuric acid and an excess of water as your solvent. The product from this reaction is again 2 diastereomeric pairs of enantiomers. We basically add water across the double bond. And I will show you another way you can make your life a little bit easier if you want to draw some of the stereochemistry, but you don't want to draw all 4 possible products. You can simply use a plus and minus to indicate the presence of the other enantiomer. Or, if you don't want to do that, and you like drawing hexagons, you can draw the other enantiomers out like this. It is also acceptable, it's also acceptable to draw the products as just straight lines without dashes or wedges, because I can't apparently talk while I'm drawing, because that communicates the same thing. Oh, dang it, Joshua. What is going on? I'm sorry for those of you in the audience who may be named Joshua. I am talking to myself instead of you. That doesn't make it better, I realize, but just weirder. So here you have the syn products, the syn diastereomers. Here you have the anti-diastereomers, where the OH and the hydrogen end up on opposite sides of the molecule. And then, of course, yeah, these two are enantiomers, and these two are enantiomers. Recall that enantiomers have to be formed in a 1-to-1 ratio, but diastereomers do not. And the mechanism is just exactly what you would expect. Alkene attacks the acid. You selectively form the new carbon-hydrogen bond, with the less substituted carbon, so that you get the more substituted carbocation. Then, in a second step, and this is just backwards SN2 chemistry, or SN1 chemistry, in a second step, water attacks the carbocation from either above or below. You get this oxonium ion intermediate, and then in a final step, the conjugate base of your acid removes a proton from the OH to give you the products that are shown. Oops, I don't want that to be. Now, I will point out that this reaction is an equilibrium. If we go from alcohol to alkene, that's elimination or dehydration of alcohols. If we go from alkene to alcohol, that's hydration of alkenes. The reason that this will go to completion is if we add an excess of water. But this is just exactly backwards from what we just barely did in chapter 9. Okay. Questions about this one? Yeah.
Sorry, can you say what the water, what the effects of the water are again?
Right. If you're going, the question is, what is the effect of water? You need water in excess to use Le Chatelier's principle to push the reaction to products. That's just a detail. That's not going to be like on an exam. If you don't click the option that has excess water, all of a sudden you get the question wrong. No. It's just to inform you why we can do this reaction in the direction that goes from olefin to alcohol instead of the direction we just barely did in chapter 9, which is alcohol goes to olefin. All right, other questions? All right. That's boring and or straightforward enough. Let's see. I'm just thinking about the next two reactions. Okay. So both hydration of alkenes and hydrohalogenation of alkenes is neither enantio or diastereoselective, but it is regioselective. You do get the Br or the OH on the more substituted carbon. The next reaction we're going to deal with is doesn't have any regioselective issues because the same type of atom gets added to both of the two carbons of the olefin, but it is diastereoselective. Diastereoselective for the anti-products. And that is we're going to choose a simple cyclohexene. In this case, it's okay if carbons 1 and 2 are identical because carbons 1 and 2 are both going to get Br anyway, so it doesn't matter. You add bromine, Br2, and the product you get is this anti-product along with its enantiomer. We don't see any syn products. So what that tells you is there is, in terms of mechanism, this tells you there's no carbocationic intermediate. All right, well, how does that look then? Let me try to give you a sense for the mechanism of the reaction. You know that there isn't a carbocation, and in terms of what you're dealing with as starting materials, your nucleophile is the olefin, so the HOMO is the carbon-carbon pi bond. The electrophile is Br2, and that means that the LUMO is the Br sigma star. So you would expect the mechanism to involve pi bond attacks Br and Br minus leaves, just like we saw in the first step for adding HBr or adding water to a double bond. However, if that's all we did, notice we would be following exactly the same pattern. We'd be making a new sigma bond, and the other carbon would get a positive charge. But we just said that can't happen because we don't see stereochemistry consistent with a carbocationic intermediate. So what likely happens is that as the pi bond is forming a new sigma bond between Br and one of these carbons, they're identical, so we don't care. Let's just say it's carbon 1. As we're forming that new carbon-bromine bond, lone pair electrons on the bromine lean back and attack the other carbon. As that carbocation would have been forming, the lone pairs on the bromine snap it up. And the product that you get, or the intermediate you get from that process, is something that looks kind of like an epoxide. This is called a bromonium ion. You can think of it as a bridged bromonium ion. Do you remember when we were doing carbocationic rearrangements, we talked about a leaning hydrogen shared between two carbons? We called that a carbonium ion. Same kind of language here with the bromine. Now, I feel like that's just a little bit confusing. So what questions do you have about this concerted process? Go ahead.
So as the pi bond attacks the bromine and the lone pairs go back to carbon 2, does that second bromine still like come off of that? Does that bond still break?
Yes, because you are, the question is, does this bond between Br and Br break? Absolutely. Because you are dumping electrons into the sigma star. This is sort of two HOMO-LUMO things happening at once. Pi bond attacks Br sigma star, and at the same time, the lone pair on Br attacks the growing carbocation on the other carbon. But it does so quickly before the carbocation has a chance to form. Other questions? Yeah?
Yeah, we point out that the bromine lone pair electrons are attacking only one of the carbons, but then we have our bridged bromonium, I guess, attached to both carbons.
Right. One of those bonds, the question is the lone pair on the Br only attacks one of those carbons, then yet we have two bonds. One of the bonds comes from pi electrons, and the other bond comes from Br lone pair electrons. Other questions? Yeah.
So when the second bromine gets kicked off into solution,
Uh-huh.
it's supposed to take those electrons with it, but those electrons are making that.
The second bromine, when it gets kicked off into solution, it takes its electrons with it. Yes. Let me draw in all the lone pairs so you can sort of see. So the bond between the two bromines breaks, and the electrons in that bond end up on Br minus. And then this lone pair that was already on the first Br is the one that does the attacking. So I should fill in the other lone pairs on that BR so that you can tell where all the electrons have gone. Yep. All right, any other questions about how this attacking process happens? It's just like the first step of the two previous reactions. The only thing we're adding is the atom that we attacked, instead of being a hydrogen, notice that hydrogen that has no lone pairs on it, the atom that we attacked was one that already had lone pairs on it. So as the new bond is forming, it's easy for that atom to snap up the carbon where a positive charge would be building up. And that's the key distinguishing feature of things that can do this. You need lone pairs on the atom that's getting attacked in the first step. All right, so we will stop there, and I will see you Wednesday. Dallin, you've asked, do the H groups on our cyclohexene have to be the same, or could one of them be a methyl group? Yeah, they could easily be methyl groups. I just chose a simple example to begin with.